All right. So the recording is in progress. So this is lecture 6. Its lecture was supposed to happen on Monday, January 26th. So things are going to get pushed back, of course. So we will still have a quiz on Friday, but the quiz on Friday will just be over partial fractions, over section 6.3. So stuff we discussed last Friday and stuff we're discussing today. You won't have a recitation on this stuff before the quiz, but we still need to have a quiz on it. So it'll just have to be a doable quiz. And then you'll have recitation resuming on this coming Tuesday. Today, January 28th, I'm here in my office most of the day. You're welcome to just come by if you want help on anything. Tomorrow, Thursday the 29th, I have my usual office hours. Also today, the 28th, Gabriel has his office hours, which are from 1 to 2. And then tomorrow I have my office hours, which are from 8 to 9:30. It's just what's on the web page. And then Friday we have class in person. We have the quiz. Friday, Gabriel has his office hours. All right. Before I start, are there any questions from any of you? All right. Well, let's get started. I'm going to join this meeting on my other device. So that's oops. Okay, doke. Now let me switch to my tablet. I want to share this device. Okay, everybody should be able to see my whiteboard now. All right. So this is lecture L06. This is Wednesday, January 28th. So again, I have office hours. Well, I'm here all day. And then Gabriel has office hours today. I'm not going to write the time because my tablet is really slow to catch up. I have office hours tomorrow. So again, Friday, we'll have quiz Q3, and it will cover just section 2.3. Partial fractions. All right. So here we go. Resume discussing partial fractions. So on Friday, we were discussing section 2.3. And I ended the class period with this example. This integral, which is 15x squared minus 6x minus 6, divided by x cubed minus x squared minus 2x. And notice that that is a proper rational function. Proper because the degree of the numerator is less than the degree of the numerator. But also notice that we don't know how to do this integral. Now, on Friday, I discuss what we do is we find what's called the partial fractions decomposition. And I just gave it to you, and I'm going to give it to you again. So this is what's called the partial fractions decomposition. Now, the thing to notice about this is that this integral, we do know how to integrate. So, I'm going to skip to the result. This is going to be 3 ln absolute value of x plus 5 ln of absolute value of x plus 1 plus 7 absolute value of ln of absolute value x minus 2 plus c. So the second two of those integrals, you need to use a substitution. But there's nothing new there. I think you've seen these kinds of things before. So today, what I want to talk about how we get these partial fractions decompositions. Well, first thing is we factor the denominator, and we make sure that the rational function is in lowest terms. So our function is 15x squared minus 6x minus 6. Divided by x cubed minus x squared minus 2x. Now, if you factor the denominator, you can factor out an x, and then what's left is a quadratic which factors easily enough as x plus 1, x minus 2. Now, the question is that fraction is that rational function in lowest terms. That is, if I were to factor the numerator, um, would either of those terms show up in the numerator? Now that can be very tedious. I'm trying to figure out if that numerator factors and what its factors are. Can take a long time. But I'm just gonna write this 15x squared minus 6x minus 6, and I'm just gonna say the numerator doesn't factor easily. The main thing is the only reason we would want to factor the numerator is if we could cancel one of the factors of the denominator. Well, you can see that there is no common factor of x in the numerator, so we wouldn't be able to cancel that. And then we could just check, are either of those other factors in the denominator a factor of the numerator? And you could just use long division and you would find out they're not. They're not factors. So if none of these factors are going to be a factor of the numerator, then we don't care to factor the numerator. So we're not going to factor it. Turns out, again, it can be factored, but its factorization is really ugly. All right, now the next thing is we build all possible basic terms for the partial fractions decomposition. What does that mean? Well, we look at the factors in this factorization. There's an x plus 1, and there's an x minus 2. Each of those is what's called a linear factor, and they're each appearing with a power of 1. So our partial fractions decomposition, we need to allow for the possibility that terms might appear with those terms in the denominator. So I'm being very vague here. I'm just going to say build all possible basic terms. So I have on the left, I have 15x squared minus 6x minus 6 divided by x. I have a tablet that is really old and it's incredibly frustrating to work with. Okay, so the denominator is x plus 1, x minus 2. So the possible terms that could appear in the partial fractions decomposition are terms that have an x in the denominator, or terms that have an x plus 1 in the denominator, or terms that have an x minus 2 in the denominator. So we need to allow that these might appear with coefficients. So these are linear factors, so the only coefficients we need to worry about are just simply constant terms that could appear up here. So an A, a B, and a C. So that's the list of all possible basic terms. I've taken each of the factors that appears in the denominator factorization, and I've made a basic term using that as a denominator. And I only include terms down here that have denominator powers less than or equal to the powers of the term in the denominator of the original fraction. Okay, now we have to figure out the values of A, B, C. Okay, well, earlier I just gave you the values. I said A is 3, B is 5, C is 7. But how do we find that? Well, there are two methods to this. Method one is, well, let's multiply both sides by x plus 1, x minus 2. So you can see when I multiply the left side by that expression, the denominator is going to cancel. So I'm going to end up with the left side being just 15x squared minus 6x minus 6. On the right, when I multiply this term by that, the x's are going to cancel. The x in the denominator is going to cancel that x in the numerator. So what's going to be left is an a multiplying the other two terms. Now think about what happens when this term multiplies this. The x plus 1 in the denominator is going to cancel that x plus 1 in the numerator. So what's going to survive is going to be b times x minus 2. And think about the third term. When I multiply that by that, the x minus 2's are going to cancel. And so I'm going to get cx x plus 1. All right, so our goal is to make this equation true. So on the left side, I have a polynomial, and on the right side, I have a polynomial. So polynomials are equal only when all of their coefficients are equal. So I've got to figure out what the coefficients are on the right side. So I'm going to do two methods. Method one is I'm going to multiply everything out on the right side, and then I'm going to match coefficients. That says match coefficients. So the left side, I have 15x squared minus 6x minus 6. On the right side, I have a times the quantity x squared minus x minus 2. That's what I get when I multiply that out. Then I get a b times x squared minus 2x. And I get a c times x squared plus x. Okay, now notice the right side is looking a little bit more like a polynomial, but I should make it a little bit clearer. I should gather up like terms. So there are a bunch of terms involving x squared. So there is an ax squared, there's a bx squared, and there's a c x squared. There are a bunch of terms involving x. There's a minus a, and there's a minus 2b, and there's a plus c, all those terms involving x. And then there's some constant terms. There's a minus 2a, and that's it. That's the only constant term. Okay, so look, we have a polynomial on the left, 15x squared minus 6x minus 6, equaling polynomial on the right side. Two polynomials are equal only when all their coefficients must match. So we have to match coefficients. So we have the coefficients of x squared have to match. We have to have 15 equaling a plus b plus c. We have to have the coefficients of x matching. We have to have minus 6 has to equal that stuff. So minus a minus 2b plus c. We have to have the coefficients of the constant terms, or they have to have the constant terms match. So minus 6 has to equal minus 2a. So notice we have three equations, three unknowns. All right, so you all know, you might have forgotten, but you all have learned how to solve equations, multiple equations and multiple unknowns. There are techniques. Anybody want to give me an idea of where to start here to find our values of ABC?
I can give one.
Yeah.
So since negative 6 is equal to negative 2a, we can solve for a right away.
Great. We get minus 6 equals minus 2a. So that means that a equals 0. All right, now let's use that information to update the previous equations.
Does A not equal 3?
A equals 3. If you want to be really picky about it, you'd say A equals 3. Okay, A equals 3. So use that to update earlier equations. So I have 15 equals 3 plus B plus C. And here I'd have minus 6 equals minus 3 minus 2B plus C. So there are my two equations. So let's clean those up. So I'd have 12 equals B plus C, and I'd have minus 9 equals minus 2B plus C. So now I have two equations and two unknowns. Okay. Did I do this
Is
right?
it is it not minus 3 equals minus 2B plus C?
Good, thank you. Minus 3. Okay, now let's subtract the second equation from the first. So when I subtract minus 3 from 12, so 12 minus a minus 3 is 15. B minus a minus 2B is 3B. And C minus C equals 0. So from this I get B is the number 5. Okay, then use that to update the equations. So I've got B equals 5, A equals 3. Okay, so we're going to use the fact that B is equal to 5 to update this equation. 12 equals B plus C. So 12 equals 5 plus C. So that tells us that C equals 7. So there's how I got earlier in I told you that, this is the partial fraction decomposition of that rational function. But I said, I just said, believe me. Well, now you can see how you find that out. You find the values of A, B, and C. Okay, so that wasn't terribly hard. So that's the end of method 1. Now, what do I mean method 1? Well, remember up here, we had multiplied both sides. We had multiplied both sides by this factor, and we'd gotten to this equation. And that's when we started method 1. Method 1 started here. We multiplied everything out, and then we matched coefficients. That will always work, but it can take a long time. So let's go back to that point where we have this equation, and we're going to do another method. So going to go back to the point where we have 15x squared minus 6x minus 6 on the left. And on the right, we have a times x plus 1, x minus 2, plus b times x minus 2, plus c times x plus 1. Now, at this point, we're going to do method 2. We're going to make clever choices of values of x. Okay, so what do I mean by that? Well, this equation equation star has to be true for all x. So any x that I want to use, if I substitute it into that equation, I'm going to get a new equation which has to be true. So let's make x equals 0. And let's substitute x equals 0 into that equation. I'm going to substitute that x equals 0 into equation star. Notice when I substitute x equals 0 into this equation, it's going to cause that term to be 0, which is going to cause that whole thing to be 0. And it's going to cause that term to be 0, which is going to cause that whole thing to be 0. And it's going to cause these two terms to be 0, which is going to make everything much simpler. So the result is going to be, I'm going to have this new equation, minus 6 equals a times 0 plus 1 times 0 minus 2. So minus 6 equals minus 2a. So I end up with a equals 3. Isn't that cool? Now let's think about another clever choice. Let's use x equal -1. We're going to sub x equals -1 into equation star. Now, when I use x equals -1, it's going to cause that term to be 0 because -1 plus 1 is 0. And that's going to kill that whole term. And it's going to cause that term to be 0, which is going to kill that whole term. So let's do that. Looks like I'm missing some parentheses here. So when I substitute x equals -1 into that equation, I get 15 times -1 squared minus 6 times -1 minus 6. I can leave off this whole term because that's going to be 0. And I can leave off that whole term because I know that's going to be 0. So I'm just going to end up with b times -1 times -1 minus 2. And so on the left, I get 15 15 plus 6 minus 6. So I get 15. And then I get b times -1 times -3 is b times 3. So I get that b is equal to 5. That matched what I got before. Now let's make another. Again, what we're doing is we're making clever choices of values of x, knowing that that black star equation has to always be true. So can anybody tell me a third value of x to use?
2.
Use x equals 2. We're going to substitute x equals 2 into that equation, black star. So notice when I substitute x equals 2 in, it's going to kill that term, which is going to kill that whole thing. And it's going to kill that term, which is going to kill that whole thing. So this whole black equation, or black star equation, gets much simpler when I use x equals 2. So 15 times 2 squared minus 6 times 2 minus 6 equals c times 2 times 2 plus 1. So I get 15 times 4 is 60 minus 12 minus 6. So 60 minus 18, so that's 42. Has to equal c times 2 times 3. So 6c. So I get that c equals 7, which is what we got before. So again, when I substitute any value of x into that equation, I get a new equation which has to be true. So you can see that this method of finding coefficients was a little bit more reliable. See if I have more pages here. Yeah, okay. So that's the end of method 2. Now, I really like method 2. I find it much simpler. The book mentions it. I forget if the book does an example. Does anybody remember if the book does any examples using method 2? All right. Well, the problem with method 2 is that it doesn't always work, or I mean, it doesn't always get you all the way. So I want to do example 2. I want to find the partial fraction decomposition for this proper rational function. In the numerator is 5x squared plus 9x minus 5. In the denominator, which is already factored, we have x minus 2 quantity squared and x squared plus 2x plus 3. Now, a couple things to notice. This is an irreducible quadratic. If you don't believe me, you can try to factor it, or you can use the quadratic formula to try to come up with roots, and you won't find any. And then, so this is an irreducible quadratic, and then this is a proper rational function. Anybody remember what proper rational function means?
The bottom fraction has a larger power than the top fraction.
Yeah, the degree of the numerator is less than the degree of the denominator. And also, this is in lowest terms. I know that because, well, I can try to divide the numerator by either one of those denominator factors using long division, and it doesn't work. I get a remainder. Or I could try to factor the numerator. It does factor, but the factors are really ugly. They involve roots. So I don't need to factor the numerator as long as I know that the thing is in lowest terms. Okay, so now I have to get the partial fractions decomposition. That involves building all the possible basic terms that might appear in the partial fraction decomposition. Well, I could have a term that has an x minus 2 in the denominator. Now notice, and that's because there is an x minus 2 over here. But notice that this term has a square. So when I build my list of all possible terms, I actually have to include another term that has an x minus 2, but being squared. So I have to include all powers up to the maximum power that appear on the left. Now, what goes in the numerator? Well, all I need to worry about in the numerator here is constants, a or b. And then I need to allow for a possible appearance of a term with that quadratic, x squared plus 2x plus 3 in the denominator. Now, it appears on the left just as power 1, so I don't need to have a higher power version of it. But in the numerator, I need to allow for the fact that there might be more than just a constant up there. There could be a cx plus d. So there's my list of all possible terms. And then so now I proceed like I did in the previous example. I'm going to multiply both sides by x plus 1 squared, or sorry, x minus 2 times x squared plus 2x plus 3. So when I do that, on the left side, when I multiply all of this by this, you can see that the denominator is going to cancel that. So I'm going to end up with just simply x squared, 5x squared plus 9x minus 5 on the left. Now, on the right side, when I multiply this term by this, that x minus 2 is going to cancel one of those factors. So what I'm going to end up with in the end is going to be an a and an x minus 2 and an x squared plus 2x minus plus 3. When I multiply b times this, that x minus 2 squared in the denominator is going to cancel that whole x minus 2 squared. So I'm going to have b times x squared plus 2x plus 3. And then think about this. When I multiply this term by this, those irreducible quadratics are going to cancel, and I'm going to end up with plus c x minus 2 squared. All right, now remember I said I like method 2. We need to figure out what a, b, c are.
Does the cx plus d just get turned into c?
Oh, nope, it doesn't. That's where I went wrong in my last meeting. Okay, so let's try method 2. Clever choices of x. Can anybody think of so type your name in the chat if you can think of a clever value of x. That's the equivalent to you raising your hand. Got one person's hand up. I'm gonna wait till 5 of you get your hands up, or type your name in the chat. Or yeah, you know how to type your name in the chat, Monica. Can I get some more hands up? What would be a clever value of x to use to simplify that expression? Trent, what's your suggestion?
You should use 2.
Okay, well, if I use x equals 2, notice it's going to kill that term, which is going to kill all of that. And it's going to kill that term, which is going to kill all of that. So that's definitely a good choice. So I'm going to have 5 times minus 2 squared plus 9 times minus 2 minus 5 equals b times minus 2 squared plus 2 times minus 2 plus 3. So 5 times 4 is 20.
We're just using x equals 2, right? Not x equals minus 2.
Oh, right. Thank you. Good. I've had a lot of coffee today, but not enough. Okay, so 5 times 4 is 20, plus 18 is 38, minus 5 is 33. On the right side, I've got 4 plus 3, that's 11. So I get that b equals 3. Great. Can anybody think of another clever choice of x? too slow. So the thing is, Trent and others notice the easy one. There's a linear factor, x minus 2, and so that's clearly going to correspond to x equals 2. But the only other factors that we have that we could exploit are this one. That's an irreducible quadratic. Irreducible means that there are no roots. So there aren't going to be any values of x that cause that to be 0. So there are no other clever choices of x. So that's a bummer. This is an example where method 2 either doesn't work at all or doesn't work very well. It got us one value, got us a value for b, but it didn't get us all the way. It didn't get us values for a, for c, or for d. But we can use this value of b to update our equation. So let's use b equals 3 to update that equation. So on the left side, we have 5x squared plus 9x minus 5. And then we have equals a times times x minus 2 times x squared plus 2x plus 3. And then we have b, which is 3 times x minus 2 squared. I'm sorry, the b times x squared plus 2x plus 3. And then we have c times cx plus d. I keep making that mistake. Cx plus d times x minus 2 squared. Okay, well, notice that each of these terms can be dragged over to the left side. So I'm going to have 5x squareds minus 3x squareds. So I'm going to have 2x squares. And then I'm going to have 9x minus 6x. So I'm going to have 3x. And I'm going to have minus 5 minus 9, which is going to be minus 14. That's what's going to happen when I move that green, all that green stuff over to the left side. And so then we have all the remaining stuff, a times x minus 2, x squared plus 2x plus 3, plus cx plus d times x minus 2 squared. All right, well, at this point, we have no choice but to just multiply everything out. So I have x times all this stuff. So a times x cubed plus 2x squared plus 3x. And then I have to have minus 2 times all this stuff. So minus 2x squared minus 4x minus 6. Okay, now over here, I have to have plus cx plus d times x squared minus 4x plus 4. So let's keep going. This is going to be a times x cubed. The x squares terms cancel, and I end up with minus x minus 6 over here. And then here I'm going to have cx cubed minus 4cx squared plus 4cx. And I'm going to have plus dx squared minus 4dx plus 4d. So let's gather up our x cubed terms. We end up with a plus c x cubed. And then our x squared terms, let's see, we have minus 4c plus d times x squared. And then our x terms, we have minus a plus 4c minus 4d. And then our constant terms, we have a minus 6a plus 4d. I'm gonna get into trouble if I make a mess, if I make that too small. I have minus 6a plus 4d times the number 1. So let's equate all of our terms. So equate the coefficients. The coefficients of x cubed have to match. So that means that, oh, look, on the left side, there's no x cubed term. On the right, there's an a plus c. Okay, the coefficients of x squared have to match. On the left, we have 2. On the right, we have minus 4c plus d. The coefficients of x have to match. On the left, we have 3. On the right, we have minus a plus 4c minus 4d. And then our constant terms. On the left, we have minus 14. On the right, we have minus 6a plus 4d. Okay, any suggestions here? We have 4 equations, 4 unknowns. Well, I'm going to walk you through this. Notice that in the first equation, from the first equation, we know that a has to equal negative c. So I can make that replacement in all the previous equations. I can use that to eliminate a. And look at the second equation. The second equation tells me that, well, I can use the second equation to get a relationship between C and D, and I can use that to eliminate D. So I'm going to just say here, the result, dot, 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 is A equals 1, B equals 3, C equals minus 1, and D equals minus 2. Oops. So again, I don't want to take up class time to do that equation, because to do that solution, because that's something you know from high school, or at least you're supposed to know. What I want to do now is I want to discuss what we would do with this information. So this is the end of finding the partial fractions decomposition. So we would use this to integrate, for instance, this 5x squared plus 9x minus 5 divided by x minus 2 squared times x squared plus 2x plus 3. So I would use that information from previous work to write these terms in the integral. 1 over x minus 2 plus 3 over x minus 2 squared plus minus x minus 2 over x squared plus 2x plus 3. So those are integrals that we know how to do. This first one, you'd have to do a substitution. You would get ln of x, absolute value of x minus 2. This integral, 3 over x minus 2 squared, you also would have to do a substitution. And you would end up with minus 3 over x minus 1. So the question is, how do we find this third integral? That's hard. Well, first thing that you can do is you can break this up into two separate integrals. So, all right, we're out of time. So I will actually, so I'm going to stop this meeting here, but I'm going to finish this problem. So in the notes that I will post for this meeting on the course webpage, you'll be able to see the solution to this problem. So that's the end of the live meeting. And also I'll stop recording. But like I said, you'll be able to find the notes for the rest of this example in the on the course webpage. So thank you all. Actually, if you all will leave, I will probably just keep recording, and then you'll be able to find the recording and the notes. But why don't you all go ahead and leave so that I could just do the recording without you all having to watch.
Thank you. Have a good one.
Thank you all.